don't know what we're doing. I'm so about to change this evolution. Words to shake the ground, you feel it moving with the revolution.
Skybet Aka Freeze. If an absolute screamer or a howler from their keeper has put you in front, don't let a lively winger on a mazy run spoil your bet. Just freeze a winning score and win a leg of your Aka early with Skybet Aka Freeze. Skybet, for the fans. Minimum 5 selections. Pre-match football only. Full-time result market only. Max stake £20. Max 3 freezes per week. Eligibility restrictions and further T&Cs apply. 18+. Gambleaware.org.
Light it up, light it up, light it up. Light it up, light it up, light it up. Cause lightning doesn't strike twice for you and I. The sun will rise tomorrow. Cause lightning doesn't strike twice for you and I.
Good evening and welcome everybody. This is Obi-Wan Pez for N-Simplex Pachinko. We are going to be working on cracking the GRE math subject test. We'll also be working on, well, specifically we'll be working on optimization problems and minima and maxima within a particular function. So have to figure out where to put stuff. Okay, so with optimization problems, we said that basically the first thing that we're going to be looking for is what is the first derivative of a particular function. And it's going to have zeros at it's going to have zeros at all critical points. Now these critical points come in three varieties. We have minima, we have maxima, and we have neither. Although the variety that we have in neither typically comes in a variety that's similar to something like y equals x cubed, where we have something that looks, roughly speaking, like this. We have a higher order of multiplicity than the other zeros. Well, they don't have to have a higher order of multiplicity, but yeah, we don't necessarily have to have a higher order of multiplicity. I'm going to have to think about that for a while. Okay, so what we have for that particular thing, right? We've got our minima, maxima, and neither, which are our zeros of the first derivative, and then we want to show what kind of critical point it is. So we've got multiple different kinds.
Don't let a lively winger on a mazy run spoil your bet. Just freeze a winning score and win a leg of your ACCA early with Skybet ACCA Freeze. Skybet, for the fans. Minimum 5 selections. Pre-match football only. Full-time result market only. Max stake £20. Max 3 freezes per week. Eligibility restrictions and further T&Cs apply. 18 plus. Gamble away.
Well, thank you for the follow. Good evening and welcome. Apologies, I'm getting fed up with something, so I just need a second here to ugh, gross. Alright, I really don't want to do that. You know, if it was like £2 a month, I probably wouldn't matter. I wouldn't mind so much, but £12 a month. Whoa. Anyway. So we're going to show what kind of critical point we've got. And in order to do that, there were a few different ways. We said one was find the second derivative. Right, we had positive, negative, and 0, or perhaps negative, 0, and positive if we wanted to go that way. Negative, 0, positive. The behavior in this case, if we have a negative second derivative, is this is concave downward. If it's positive, then we have a concave upward. And if the sign is 0, then it's linear at that particular point. Right, the inflection point could be that we have something that's concave downward this way, concave upward this way. And so now, because we have this changing concavity, changing curvature, we must have a point somewhere in the middle that's a 0. Okay. Other options that we had looked at look at the surrounding values, because again, if they're the same, that's either going to be a maximum or a minimum, depending on which way the points immediately surrounding it go. It's going to be a critical point, but it will not be a minimum or maximum. So you do have to be careful when you're doing stuff like this, just to make sure that you're not getting bits and pieces all confused with each other. Okay. Let's see, last time we did talk about the sum of two non-negative numbers, x and y, is 12. What's the largest possible product of x squared and y? So x squared times y gives us a product p, or z function, or objective function, or something like that. And then we try to figure out what the first derivative's zeros are going to be in terms of one of the variables. Because we had a system of equations, we could fit in y is equal to 12 minus x, replace y in the other equation, and then it's all in terms of x. So take the derivative, super easy. And then we had a rectangle in the fourth quadrant of the xy plane, has adjacent sides on the coordinate axes. If the vertex opposite the origin is on the curve, y equals log of x, what's the maximum area this rectangle can have? So in that particular case, we had a nice little diagram going, right? This was log of x goes something like this, and we had a rectangle which looked basically like this. And then what is the maximum area that this rectangle can attain? And that one is a product of E, which is not really surprising at all. Okay. So for a couple of other optimization type things, we have a series of problems which are called related rates. Related rates are just going to talk about so for instance, if we had the old classic one, if a ladder is leaning up against a wall and the bottom is resting on a patch of ice, it's fine when it's just sitting there, but the second a person stands on it, that weight is now going to press down, which is going to impart an outward force, and then the frictional force, it being on ice, is not going to be sufficient in holding the ladder in place. So this is now going to go outward. Let's say this is a 15-foot ladder.
Skybet Aka freeze. If an absolute screamer or a howler from their keeper has put you in front,
starts moving when it is 2 feet from the wall.
Skybet Aka freeze. Skybet for the fans. Minimum 3 match only. Full-time result market only. Max stake £20. Max 3 freezes per week. Eligibility restrictions and further T&Cs apply. 18+. Gambleaware.org.
And it starts moving outward with a rate of or I guess it starts at 0, but when we first, get a bead on what's going on here, this is going to start moving outward at a rate of 5 feet per second, which then means that because this is moving outward, the ladder, which is now touching the wall, will continue to touch the wall, but end up sliding down it. So, when the bottom of the ladder is 2 feet away from the wall, and assuming that the wall is appropriately plumb, and it's 15 feet long, when the ladder is moving at a rate of 5 feet per second at 2 feet away from the wall, how fast is it moving down the wall? Okay, so we have two sets of information here. We have distances, but then we also have a rate. So we know that this is going to be in feet per second for both the top of the ladder moving down and also the bottom of the ladder moving out. So we have those two pieces of information, and then we want to know at the given scenario, when this particular scenario is happening, what is this rate going to be? Okay, so first off, we want to start with any sort of relationships that we know exist. So this being correctly plumb to the wall, the floor being correctly plumb to the wall, it's going to have a right angle in it, which then naturally the 15-foot ladder makes a right triangle out of this. So we do know that y squared plus 2 squared, being the x distance, is going to be equal to 15 squared. So we know that that's true. Which means that y squared is going to be equal to 225 minus 4 is 221. And so y is going to be the square root of 221 feet. So just under 15. We knew it was going to be pretty close anyway, but nonetheless, right? Okay, now how do we deal with rates? Well, we had been learning in the calculus thus far that every time we start dealing with distances, we can then start dealing with velocities as the derivatives of distance functions. And just to complete the diagram, if we take the derivative again, this ends up with an acceleration function. Okay, so in this particular case, this is really our process. We would need to start with the distance function, take its derivative, get the velocity function, and in this case, the velocity value is going to be fairly easily found from velocity value will be found from the other velocity value and the other velocity that we have. So overall, the function that we have here, which, yeah, it's a function. It just doesn't look like one when you start, is going to be that x squared plus y squared equals 15 squared. So we remove the 2 that we had from before because that is a particular scenario. This x squared plus y squared equals 15 squared is true no matter where in the process we are. So we could have set this up against the building, we could have started moving it out a bit, we could have set it in motion to move most of the way down the building. All that's true. So with this, and this is really one of the tools that benefits calculus so much, is that when we take a situation and we look at it as a whole, let me also, apologies. drop this in chat because I meant to do that earlier. This is no copyright sounds. Pretty decent playlist. Not lo-fi. And also tons of ads at this point. That's not their fault. Right, so this is true no matter where in this process we are. So, could be anywhere.
And that's not all. They've got incredible offers like early payouts and so much payoff.
Why would you want to build a bet anywhere else? Download the app and see why it's never ordinary at Bet365.
It's ridiculous. I really also hate, absolutely hate, the overabundance of gambling ads at the moment. It's a horrible, horrible industry as a whole, and I can speak out like that because, quite frankly, just don't care. They are not sponsoring me, and I will absolutely never, ever accept a sponsorship from a gambling company. Especially if they would want to be like, yeah, you need to, like, tout our services. And man, are you barking up the wrong tree? Alright. So what we can do here is take the generic derivative of all of this stuff, and we end up with the derivative of x squared is going to be 2x times, use the chain rule, the derivative of the thing on the inside, which is dx, plus same deal here, 2y dy is equal to the derivative of a constant, 225, is just going to be 0. Now the thing we're looking for is the derivative, or the velocity in this case, of the y direction compared to the x direction. So here we want dy dx. So rearrange this stuff so that you get dy dx. We're going to have 2y dy is equal to negative 2x dx. So dy dx is going to be equal to negative 2x over 2y, which is negative x over y. Alright, and this is going to be in feet per second. This does not mean that our x's are in feet and our y's are in seconds. It doesn't work like that. This is just saying that in order to compare our velocities, we end up with these two things. Our x and our y, which are distances, put in ratio, which get us a unit of feet per second. So dy dx is equal to negative, our x distance was 2 feet. Our y distance was root 221. Okay, and next question. Where did the calculator go? Probably just put it right here. And no, not really. Oh, right there. It is a negative 0.1345 feet per second. Actually, that's not true, is it? It's feet per... It is actually feet per feet. Hang on. That's right. Because we're not taking the derivative with respect to... I just completely left out the 5 feet per second as... Here's the other thing, right? Right, this is dy, if I thought about this carefully, dy dt. And this one down here, 5 feet per second, is dx dt. So here we do actually see that this should be, in fact, not the generic derivative, but rather the derivative with respect to time, d dt. Okay. Good news, it only takes a little tiny bit of correction. Okay, this is going to require a little bit more. Okay, so dy dt is going to be equal to negative 2x over 2y times dx dt. And this is ever so slightly off, but pretty much right. Negative x over y times dx dt. Okay, so negative x over y is still negative 2 over root 221. However, then we get a 5 feet per second attached with dx dt. Okay, and that value is approximately 5 times as much as the previous one. Literally the same. 0.6727, give or take, feet per second. That's how you handle mistakes in your classroom. Own up, fix it, make a bigger deal of the fact that this is the correct answer now. Admit your mistakes, but don't harp on them. Okay, so this is still less than 1 foot per second, roughly speaking 2/3 of a foot per second. Not too bad. However, at what speed will the ladder hit the ground? So this gets to be a little more interesting. Because if we look at what we did just beforehand, right, so here what we get is dy dt is going to be equal to negative x over y times dx dt. Good evening and welcome everybody from Zach's channel, E to the 2I Pi. My name is Obi-Wan Pez. This is N Simplex Pachinko. All of you awesome people over there. How you doing? Whoa. That's as loud as I am. So, I hope you all are having a good evening. What'd you get up to tonight? So this becomes an interesting problem, because at what speed will the ladder hit the ground? Tanzuru? Zero. Zach referred you to me for math. Excellent. Fizzbuzz, Crystal Storms, good evening and welcome. Thank you so much for the follow. As I said, my name is Obi-Wan Pez. This is N Simplex Pachinko. We have done mathematic type stuff since about 2021 here on Twitch. I have been a 15-year math teacher at a community college in Maryland in the United States. So I taught everywhere from like basic math all the way through differential equations. And over my 15 years, I've been working with a couple of different styles of teaching. My first was essentially a Socratic type method where I would ask a lot of questions and then lead the students through a bunch of stuff. I fairly quickly found out that I was only actually talking with about 2 people at a time. And you know, that's not great for engagement in your classroom. Over the years, I tried working on that, getting out of my shell a little bit, but nothing quite worked. And in 2022, went to the AMATIC, American Mathematical Association of Two-Year Colleges, teaching conference in Toronto in Canada, and met this guy, Peter Liljedahl, who does this thing, Building Thinking Classrooms, which is a much more engaged style to get out into the classroom and like essentially you are facilitating the class rather than lecturing the entire time. And it is amazing and wild. If you could do it right, it's amazing. It fits. It works every single day. Give or take. Nothing works every single day, but nonetheless. I've been doing a series on that one in order to try and parse through how educators can start using Building Thinking Classrooms, what my experiences were in the classroom, and try to get a better handle on like how to do stuff with it. I think after we're done with the book, I would like to do a few planning sessions whenever I feel like it to start getting actual lesson plans together for specific classes. So we'll see how it goes. Hard work pays off. It definitely does. So you do have to actually get into the weeds and start like really doing the hard work as an educator. De-emulator. Oh, nice. Absolutely, sir. So that's going to be on Monday nights. Wednesday nights are our calculation nights. So if you have any particular questions, I dedicate my Wednesdays to specifically answering math questions. If you would like to know why something works, I am probably your guy. With, you know, with respect to everybody else, yeah, everybody's really awesome. But I have been working really hard for the last 10-ish years on trying to make sure that everybody understands why something works. And it's going to take a while, but but I found that making sure that all of those students, making sure that they understand why something works ends up hammering home the idea a lot better. Any theories? How do you mean? Closed integration. So I've only really done, like, I've done classes up through master's level of mathematics, but ask away on what you find interesting. Sure, on the with the understanding that I do only really teach through differential equations. So once you start getting into like the higher levels of mathematics, when you start getting into undergraduate and then graduate mathematics, like there's a lot of gaps. It's been about 20 years since my it's been 15 years since the completion of my master's. You can't just memorize all the trinomials that the teachers ask about and then say you know factoring. What? I know, right? Okay. So, yeah, like I said, as long as it's something that I have taught before, which means through differential equations, I should not have any trouble reasonably understanding how to teach that particular section. I am not a faculty member anymore, so I left my position at the community college where I was an associate professor in December 2023, January 2024. As of April 2024, my family moved to the UK. That's here. We live in North Yorkshire, which is fairly north in the country. Pretty close to the 54 degrees north parallel line. And it gets very dark in winter and it gets very bright in summer, so much so that when I'm streaming, that window never actually gets dark in like June, July. It's crazy. I love it. If you give some options, absolutely. You're in Scotland? Nice. So yes, you know exactly what I'm talking about. Hey Famish, how's it going? Yep, so we make regular trips out here to places around like Leeds, York, various other locations, and yeah, just hang out. So I am attempting to get a few different things going in terms of like projects. One is to get my teaching portfolio more grounded in building thinking classrooms. So like Zach said, you know, if we do a work session sometime, that would be amazing, and I'd love to invite anybody who wants to come on in. We're also going to, on my end, I also want to look into more of the Common Core stuff and start looking at how to teach Common Core, and then do videos on YouTube about how to teach Common Core as an educator and as a parent. Am I looking to reapply for faculty positions? I don't know what I want to do with the rest of my life is the problem. There is a part of me that's pulling back to academia. There is a part of me that's actually pulling, and this is going to be a little weird, but pulling into politics. There's a part of me that's saying, like, never mind any of this and go to industry. Like, I've got so much tearing at me in every direction at this point. I don't know what I want to do. Politics from a mathematician, I know. Cedric Villani, the Fields Medal winner not so many years ago, actually ran in France. Became a, I'm not sure exactly what level he was at, but senator of some kind. Stayed for one term and then ended up not running again. I think he was already disillusioned, unfortunately. So yeah, I've got stuff yanking in all directions. I don't know what I want to do, but either way, you know, no matter what, I definitely want to still do math. So highest maths you've studied is AP level, so like calculus, stats is usually AP level, like college level. Do enjoy some theories that are higher than what Scottish high school education is. Yeah. I mean, you could go for it. Well, let's see where it lands. Got to work on some game dev projects. Build up your resume, yeah. So here what we've got is... oh, and that's the other thing I need to work out, Crystal. Thank you for also sort of reminding me. Is I want to actually figure out the structure of math education here in the UK. Because it's kind of, at least at my kids' school, it's kind of like they build on like difficulty of problems rather than subject. Build a game based on math. Be nice. Consider wet. It is fairly often rainy, foggy, overcast, which is what you hear anyway. But, you know, yeah, cold. We have been hitting 10 degrees Celsius overnight, so that's 40 something, 18 above 32. Yeah. Could be up to 50. So it's pretty consistently like 40s and 50s overnight. And then during the day it gets up to maybe 20 degrees, which is 65, 68. Gotta get a good setup, yeah. But I'm also from New England originally, which is in the United States, Northeast region, where this time of year, the leaves have pretty much already started changing. First frost is usually in the next 5 days, although these days I don't. This was before global warming was a big thing. Yeah, first frost would usually be in the next 5 days, and we'll be back to school, and you'd be breaking out. You would have already broken out your sweatshirts and light jackets. So, you know, I understand everybody's accents just fine. The thing that gets me, even still to this day, is when somebody in Yorkshire says, "You're right." Because that's usually their first interaction with you, which is not, "Are you feeling all right?" It is basically, "Hi." But I keep thinking of "you're right" as, how are you doing? Are you feeling fine? And I'm like, well, yeah, I'm okay. I get right. That's not what you meant by that. Cool. El Salvador. Pupusas. Nice. That'd be so good. All right, so for our calculus here, and again, feel free to ask any other questions. I'll dive into it as we get to it.
Never too early for Christmas.
At what speed will the ladder hit the ground when you're looking at something like this?
Listen now on Spotify.
What's going to happen is that our
All hands with their best ever
dy dt will increase as the ladder keeps sliding outward. The top is going to fall faster and faster. It's never really going to exceed the, or at least it shouldn't exceed the speed of gravity there. But ladder should have been on the ground to begin with. I mean, it's leaning up against the wall. Hey, high potential, how you doing? So dy dt is going to increase in the negative direction. I guess that's decrease. But let me tell you, if you're on the ladder while it's doing this, it's definitely an increase. And your dx dt is going to decrease. It's going to be positive, but it's going to be going to 0. Now, interestingly enough, right, when you start looking at something like this, your x is going to start approaching 15 feet. Your y value, on the other hand, is going to start approaching 0. Which means that our dy dt is going to increase at a faster and faster and faster rate, potentially making this fraction go to negative infinity. And I can guarantee you're not going to beat the speed of sound. You're probably not even going to beat somebody who fell, or the paintbrush that you dropped from the top of the ladder when you started slipping, because you definitely are going to go and drop everything. So there's something here that's not quite right. Now, the other thing that we do have is that this part is also going to 0. So because we have a denominator that's going to 0 with a multiplier that's also going to 0, these two things are probably going to be close-ish to dividing out. We're not going to actually worry about that quite like 100%. So instead, what we want to look at is more or less what's going to happen in the limiting case. So right, so since at the very least this is going to start approaching, well, it's going to become an indeterminate value. It's going to be 0 over 0 in the limit. So when y goes as close to 0 as we possibly can, and dx dt is going to start slowing down as you slide out further and further and further. Right? It's an indeterminate value. It's going to 0 over 0. So let's look at the limiting case here. We do know that dx dt and dy dt have this particular relationship. Now I think I kind of ruined myself here because we can't actually figure out this solution because of this. However, there should be a way to figure it out. Put a ladder onto the ladder of that ladder and a floor on top of another ladder. I mean, obviously. Yeah, so the main issue here again is that we have these 4 variables that are here. So again, that's going to be the actual problem. However, if we come out with, like I said, if we do a limiting case, so we get values that are really, really close. Yeah, so the velocity function is going to describe the v of t for that particular x of t. Now, it is also possible that I just lied when I started doing this thing, but it's okay. Because I made up the original value, right? That it was going to be 5 meters per second, or 5 feet per second, going outward at the initial 2-foot distance. And there's no constants here which are like gonna mitigate all of this stuff. So it's not like I could even work out what the actual distance function is to then like work out the appropriate velocity function. Like we already have the velocity function. It's this dy dt dx dt thing. Okay, so we have dy dt is equal to, here again we know that we have the limit x goes to 15 of x over, I mean this is not really gonna help all that much, but gross. Yeah, the issue is we have too many variables, because this is going to approach just what is the relationship between dy dt and dx dt, which we don't actually have a real relationship between them. We have a relative relationship between them. Realistically, we could figure this out if we knew enough physics about the icy surface, etc., etc. That's one of the other problems with this. So here we did not, well, actually, we did not want to do ydx. Oops. Okay. So one way to do it is to actually calculate out what we would get in the case of an x and a y and a dx dt as like our multiple independent variables. So this is like, 14. This would be the square root of 196 from 225 is going to be, what, 29? Right, and then we're still going to have problems here because we don't actually know what dx dt is going to be. Good times. All right, so I made stuff up and we got into some trouble there. It's fine. We'll work it out when I get back. Ads are about to start. Crystal, you said in particular always in liked imaginary numbers, Pascal's triangle, golden ratio. Want to know more about quantum stuff? Oh dear. So I have done work with Pascal's triangle. You might be able to figure it out from my name. Specifically, I did some extension research work with some of the students who were at my community college. When I was a professor, they were students. Wherein we did a bunch of work on trying to figure out the patterns that existed in, the Pascal triangle in higher dimensions. So I did some independent work that was trying to figure out some of the relationships that exist there, and then other people were working specifically in 3 dimensions and to try to work out relationships there. I can explain when I get back. So we'll be right back. 3 minutes. I gotta go check laundry and all that other stuff. So see you in a bit. Thanks for coming.
Like a broken soul.
There are some things you'll never understand, like why did that person ghost me? When did manspreading become socially acceptable? And how come that dinosaur theme park keeps reopening, given its safety record? But some things you can understand, like your Experian credit score. The more you improve your score, the more you could save on things like credit cards, car loans, mobile contracts, and more. It's dead easy to check and completely free. Download the Experian app and check your score today.
Alrighty, welcome back. Alright, so now get to see my messy room. On a, stream by stream basis, we do martial arts here as well. So, oh hell, a little bit of each, I guess. So, to do some Tai Chi warm-ups, kind of let your arms flow with the movement of your weight. Basically, if I just let them go, they're going to swing until they stop. But then if I just shift weight back and forth, it's a bit like when you're on a swing set, something like that. Try to let your arms just kind of flop a little bit. And this increases the blood flow. It also increases the it's not flow, but the not preponderance. Come on. Increases the synovial fluid movement through some of your joints and stuff like that, which is really good for them. As long as you're not actually doing any harm, damage, whatever, because there's like none in there now, it's actually really good for you. So, and we also do side to side, so we kind of. Oh, yeah, come on. What are we doing? There we go. Again, here we just kind of dip a little bit, and it sends the front arm kind of swinging out. The back arm just kind of goes with it. And then once you're sufficiently warmed up with that, usually we also go to what's called bear. So we put our feet parallel facing front, right about shoulder width, maybe a little bit more. Put our arms out like a bear. And then we turn to one side. Usually put weight on one foot, turn toward that side, and then once you're turned pretty much the opposite direction, we sink back onto the other foot. At here, we want to make sure that our weight is not, our weight is like 90% on one leg every time that we do this, but we also don't want to lean too far. We want to make sure that our weight is like over the base foot, or just a little bit inside of it. So we go like this, back up until we hit about here, and then turn, keep the weight on that foot, and then back up into it being on the other foot. And then we just keep doing this over and over, nice and slowly. We're basically pushing off of what is our front leg to be able to turn, and then let that be the back leg. We didn't do our requisite Tai Chi last night, so, we had the Tai Chi game. I just kept blowing through ads because I was so caught up in the game itself. Alright, then once we get that, do that a whole bunch of times. I think the music is possibly driving me going a little bit faster. Gotta stop doing that. Then once we've done that, the other way to do this is to use that, but also then have your arms follow along with it rather than just be out like a bear. Here we're going to bring the front arm out in sort of a warding position. You're doing a ward off, while at the same time this one's going to follow along with it. Turn, shift, and then we're going to swap and go back this way. So when we do this, this gets more of our motions together. We're putting more of our weight on the feet in the appropriate locations, and we're also doing the arm movements. We're doing the turns when it's appropriate. We're still backing mostly into sort of a defensive stance with all this stuff. And then this works out pretty well because we do the first form, which involves all 4 moves in the orthogonal directions and all 4 moves in the diagonal directions. The orthogonal directions are what to do when you're in control of the situation, and the diagonal directions are what to do when you're not in control of the situation. So, typically, first move is a step out to the side with using our energy ball that we bring across with us. There is no actual energy here. I'm a spoil sport, I know. But at the same time, what we're doing is we're bringing all of the pieces of our body into place. We're sitting our body down and pushing out with our legs. And this causes a double-weighted feeling, which also makes it really hard to move you forcibly. So even if you're not that big, okay, what we do first is we step up to the front and do a ward off. So this is blocking. You're usually putting forearm to forearm with your opponent. And then here, this is completing the frame. So this keeps you to make sure that you have the proper, there we go, keep your body straight. Once we reach this position, we turn further, sink back, and bring the backhand about to mid forearm. And we do a roll back. So this comes back like this. It's more or less going to parry an attack that's coming in. And then we do a press. We bring all of our weight to the front foot. Push out like this just gently, or break our hands apart. Sink back onto the back foot, which puts all of that energy into the back foot. And then we do a push, which brings everything up to the front leg. Again, this is like, I'm too far apart here, I think. This is going to use not just like a push, but you're going to actually, when you start from here, you use your entire body weight to push into whatever your target is. So using your entire body weight is going to be much more powerful. And typically what this ends up actually looking like when you're doing this is you're going to come into something like this. You're going to sink back on the back foot, and you're going to, oop, that was terrible. You're going to sink back onto the back foot, double weight, and then you're going to go like this. Now, keep in mind, I weigh under 200 pounds, but when you get something that is moving with 200 pounds of weight and pushing into you, that's pretty significant, especially if somebody actually knows what the hell they're doing. So we're pushing down with both of our legs, And then here we just lift up the front one, and all of that force on the back leg then gets sprung outward. So we do our roll back and press and then push. And then here, this is where we break from the orthogonal directions and we say, now we're going to do things in diagonal directions. So the first one is a pluck. So generally speaking, somebody's coming at you. You are also parrying, but rather than letting it go past you and then using that energy, you actually move it. Oftentimes either grabbing the wrist and pulling harder, or you parry and move with it. So here we're here, we parry with it. And then we do what's called a split, which usually involves absolutely smacking the hell out of somebody's face. If somebody is actually attacking you and you do something like that, which then hits them across the face, they're probably not going to be attacking you for much longer. We also slap here to stop the arm motion. The hand keeps going though, because it creates essentially a whip. So all of the energy that's coming across like this with the shoulder now gets translated into just the hand. So once you do a split, then what we do is we say, if this person then grabbed your wrist, you do a clear. So we take our other hand, which is currently on our forearm, and essentially like wrap your hand around your own arm and clear their, yank your hand back and clear whatever they were holding on to you with. So they're not here anymore. Then, because we're mostly on our back foot, we move forward to our front foot again and elbow. This could either be grabbing like back of a neck, collar of a shirt, or all sorts of stuff, but you're here, and then you put in the necessary force. All right, and then the last one is a shoulder strike, where we step back gently and then pop forward like this. Normally you take your shoulder, you drive it into the other person. You're aiming for a chest or a solar plexus being the big one. If you can hit a person here, they're not going to be doing much. But especially if you drive this into their solar plexus at a short distance, they're not going to be able to breathe very well. Also, this is going to swing nice and gently here. So we hit with the shoulder and also we let this fly. Odds are your attacker is a male. And that's pretty effective too. From there, we then just go straight to ward off, roll back, press, push, pluck, split, elbow, shoulder. You can keep doing that all the way across a room. The other one that we do in our Tai Chi class is that we start with our... Oh no, that was it. We start with the rollback and move up. We do... I'm sorry, that's a ward off. We do a ward off, we move up. We do a rollback, press, move up, push, move up, pluck, split, yeah, elbow, we move up, shoulder, we only move back a little bit, and then we keep advancing every move. We keep moving up. And then just for fun, because I didn't do anything last night, I was really lazy. We'll also do a karate form. Let's do Pinan 3. This is from Tang Sudo Karate. Pinan 3 is like a going for blue belt, I think. You're usually a green belt going for blue. So we start with a Junbi, and then we go into an inside-out block. We step up and punch. This is usually also very devastating. And then we pop our hips back and do both an up block and a down block at the same time. Same on this side. And again. And then we... and then we do an inside-out block to the other side. Oops. Should be in Fugal stance, which is a defensive stance. Back legs at 45-degree angle backward. Front leg is forward, and there's like an 85-15 ratio on your weight. So here, no, we're there. And then same. And then from here we do a twin fist to the front. And a, let's see. This does a chop. Which way are we going? Yeah, so we do a twin fist, followed by a chop, wrap, chop, and then we square up in the opposite direction. And then tension down. This is where it gets a little bit hard, and everybody's going to be staring at my... So here we do a hands on hips, essentially, crescent kick, Kima stance. We've got somebody who's going to punch at us, so what we do is we use our shoulder as a parry, and then do a back fist, bring it back, crescent kick, parry, back fist, crescent kick, parry, back fist, square up Kima, punch to the back of the room, essentially. And then we turn around, punch over the shoulder as well as elbow back, and then we jump to the right. Normally a little bit bigger of a place here to work with, and then do the same on the other side. And that's the end of the form. Back to Jumbi. So Tang Sudo Karate is a nice little martial art, originally made famous in America by Chuck Norris. No, I have not met Chuck Norris. No, it is not, he is not technically affiliated with anything that I do. Although I did have a realtor named Chuck Norris. No relation, because that wasn't his last name. Which equation describes this? Yeah. There are a lot of partial differential equations, nonlinear differential equations, and I'm sure there's like a karate notation that somebody has come up with. We could also say that there's most likely some bits of tensor calculus. Ayo. All right. Well, thank you for indulging me, everybody. So I have an interesting idea. dy dt is equal to, I'm sure this doesn't work. No. Okay, let's call dy dt v is equal to, tell you what, v in the second direction is equal to negative x over y was 14 over square root 29. V1. And we can go one better. We can go one better. We can turn this into x. No, let's not do x. Let's turn this into a. We can call this 220, the square root of 225 minus a squared. Create a slider for a. And we want to know what happens as a starts approaching 0 from a small number. Not quite what I was expecting. No. Wait. A is close to 15. Yeah, that's the problem, right? We want to know what's going on there. And if we try to translate this into polar coordinates, we're going to have the same problem. I think we need physics to do it for real, but... Alright, we will... I asked the wrong question, right? It's just a matter of, like, we made it too complicated. Okay. So at any rate, we can do this if we know what the distance x is going to be. We can find the distance y, not difficult, and then we can, if we're told what dx dt is at any given moment in time, we will then be able to find dy dt at that time. So this is when dy dt when x is 2 feet. And dx dt is 5 feet per second. So like those two pieces of information end up being crucial to being able to figure out what dy dt is in that particular case. Okay. So I promised you all a little bit on my name. So we were working out as a group. What happens?
There are some things you'll never understand. Like, why did that person ghost me? When did manspreading become socially acceptable? And how come that dinosaur theme park keeps reopening, given its safety record?
As this goes further and further out, we know that we are able to find any particular value on this by calling it
Download the Experian app and check your score today.
The n direction is going to be how many steps in are we going, where the first one is n equals 0, and the last one is n equals r, where r equals 0 at the top, r equals 1, r equals 2, etc. I think I did this a slightly different way than I'm used to, but it's fine. It all works out in the end. So let me just check here. So this is going to be n equals 0, and then n equals 1, which is the same as r. Yes. Okay, good. Same as when we go all the way down. R equals 1, 2, 3, 4, 5, 6. And in this particular row, right, this is going to be 6. So 0, 1, 2, 3, 4, 5, 6. Cool. This is better known as a choose function. So the way that this works is when you say, okay, you're going to choose A or B at every particular decision point, if you will. So my mind immediately went to The Price is Right, which is the American television game show from middays on CBS. And they have a particular game called Plinko, which is copyrighted, trademarked, whatever. And I said, "Oh, that's kind of like Plinko. We could talk about that in terms of, you know, this particular game. It's kind of neat. Your decisions are left or right. And you, personally, don't have to make this decision. You could get, you know, something else to do it for you. Be it a coin flip, which is also what this is often seen in terms of, or making decisions on turning left and turning right on, you know, roads, or in this particular case, on a Plinko board. I then also remembered that the generic name for Plinko is pachinko. The pachinko machines in particularly Japanese gambling halls are have little steel pegs which are in rows, and the ball goes down through all of those little holes between the pegs, and then can go into a chute. The chute then allows you to either win or lose money based on how much money you put in, all this other stuff. So, I was looking at this and realized that, oh, this is just like coin flipping. The probability of getting heads versus tails, you know, the probability of getting no heads out of 6 flips is going to be 1 out of the sum of that row. I think that one's 216. No. Jeez. 20, 50, 62, 64. Yeah. So this is 2 to the 6th is going to be the total. All right, 2 to the 6 is 64 for that row. It's going to be 32 for the one above it, 16 for the one above it, etc. So the total possibilities are powers of 2. The total number of successes depends on what you're aiming for. So if I want, you know, at least 2 heads, this was 0, this is 1, this is 2, and 3, 4, and 5 heads out of 5 flips. I would sum these up. It's going to be 26 out of 32 is the likelihood of getting at least 2 heads in 5 flips. Okay, so basic Pascal triangle, all that good stuff. Our students had also wondered what would happen if you... Oops. What would happen if you start looking at this in 3 dimensions? So now you have 3 possibilities. From this particular point, you could go in the A direction, in the B direction, or in the C direction. So from here, we go A, we go B, or we go C. So then how would you describe how to get to any particular location? Well, in this particular case, if we went 1 in the A direction, we'd be here. And then if we go 1 in the B direction, we would go to the right and down, which ends up here at this location. Or if we had started in the B direction and then gone in the A direction, we'd end up here. So each of these individual values that we find are going to be the number of different paths that we could take to get to that same location after that same number of flips, in this case, with this number of sides on our coin. So here, right, this is 1A, 1B. This is 1A, 1B. This is 1B, 1C. This is 2C. This is 2A. This is 2B. And this is 1A, 1C. So then how do we codify this and try to get it into like actual mathematical notation? How do we use the choose notation from up above? Well, I figured out, and this took a little bit of time. I was in the car. It was my spouse's turn to drive, so I pulled out my notebook and I just started scribbling all over the place. And I realized, like, I had a couple of realizations. I was like, wait, we don't have to figure out... we don't have to figure out, like, a whole bunch of stuff. We have all the information we need. Just like with our choose formula, any particular NCR is going to be equal to n factorial. Ah, shoot. I got to do it backwards because the row factorial that we're on divided by n factorial r minus n factorial. Right, so now we want, like, what row are we on? Right, let's say we want 20. Okay, we want to know what's going to happen when we choose 0, 1, 2, n equals 3. So how many different ways are there to get 3 heads out of 6 flips? Right, number of heads, or number of lefts, whatever it might be. So here, with the n choose r formula, we said we're going to do 3 choose 6 to try to figure it out. It should be 20, right? So if I messed up this formula, we're going to know pretty quick. Okay, this is going to be 6 factorial. which should be 720. Okay, divided by n was 3 factorial times, this is now r minus n is 6 minus 3 factorial, which is also 3 factorial. So 3 factorial, which are each 6. So it's 720 over 6 times 6, or 720 over 36. However you want to do it, right? 36 into 72 goes twice, and then we have none left over. And we have an extra 0 to deal with. So 3 choose 6 gets us 20, and that's exactly what we need to do. And then I had the realization that, or rather, the way that I always saw it was that this n is our target, and this r minus n is left over. My realization was that when I moved to a 3-dimensional case, we're kind of doing the same thing. We still have the same number of flips. But we still have the same number of flips, so r factorial isn't going to change here. But what's going to change is the denominator. We choose what's in the first group, n factorial. And then the other stuff that exists, the leftovers, come in many different varieties. So there's what's in the second bin, factorial. What's in the third bin, factorial. So this is really, you're choosing what all of the bin sizes are, n sub I. And then here, we're just saying, what do these sizes need to be? And I had this moment of clarity where I was like, that's it. That's how we do it. And I like calculated out a whole bunch of examples, and they all worked 100%. So when we got back to civilization, because we were up in upstate New York, when we got back onto my spouse's father's Wi-Fi, I looked it up, and sure enough, this is the multinomial. And it's been known since the 1800s. Like, just, I was like, oh, come on, man. First time that I actually find something on my own, and of course it's been known for 200 years. So now, I grant you, this is not hard mathematics, right? This is simple stuff when you start thinking about it in terms of, like, Pascal triangle and all that. And you're just saying, I want this many bins, right? I is the number of bins we're choosing. Number of distinct objects. Or bins. So this is it. And I said, okay, well now I can find all of the numbers arithmetically. I could just go in and manually say, hey, computer, I want you to pick all of the different partitions of this particular number and put them into these things, and we can also separate it and say, I know that this is going to be symmetric, so like we don't need to do all of the numbers on this particular slice. We could just say, find me all the different ones. So if you know, if the if the number of objects, if the number of each n1, n2, n3, etc. ends up being, I forget, like the sum of all of them needs to be r. That's given. And then it was a matter of like, just do different partitions of it. I don't remember how I did it, but I plugged something into, you know, Python or whatever, and tried to figure out how to make that work. This was a long time ago. It's like 2015, 2016, I think. But we figured out in a number of different ways that there are some nice patterns that exist. So, for instance, as we're choosing which directions to move in, we're always going to end up with the Pascal triangle on each of the faces of the three-dimensional tetrahedron. Right, the Pascal triangle is the 2-simplex. The tetrahedron is a 3-simplex. And then when we start moving up into higher dimensions, we run out of names pretty quickly. So it's going to be the 4-simplex, the 5-simplex, the 6-simplex, in order to figure out, you know, what dimensionality we're using. Yeah, so from here, we'll notice that we also get the same thing that we got on the Pascal. We get 1, 4, 6, 4, 1 as what's on the face, and then all subsequent faces as well. Right, so you get 1, 4, 6, 4, 1 on all three of the faces, and then what? Well, we know that these three are all going to drop into one bin, and that is right here. So all three of these could potentially drop into that circle. So what's the number that's there? How many paths do we take in order to get to that location? It's the sum of those three. Right? 3 paths get us to this 3, 3 paths get us to this 3, and 6 paths get us to that 6. So those together, if they drop into this last circle at the bottom, has to get us 12 different paths to get here. And then the same is true for this 12 here, and this 12 here. And then that's all the possibilities that we end up getting. There aren't any more. There's nothing in the middle here. There is no middle. This actually ends up packing a tetrahedron in this place. I also know that this is going to pack a tetrahedron because I have another apex of a tetrahedron right here. That 6 is then going to go down into each of the 12s. And now we can start a new tetrahedron starting from 6, 12, 12, 12, and going on further. It doesn't actually exist. Like, that does not have necessarily the same meaning, but it's an interesting thing. You could also get the numbers on the next layer and the next layer and the next layer by doing some interesting math. So, right. So anyway, this keeps going, and we can get all of those numbers again by working out the partitions. It also makes sense that the faces are going to have the same as the original Pascal triangle, because all that's going to happen is that the first two numbers, n1 and n2, are going to have values in them, whereas n3 is going to be all 0. So of course the front face is all A's and B's, right? Is all n1 and n2. There's no n3 involved. And then along the back side, we've got B's and C's. So that's n2 and n3. And then the other side, it's backwards from how you do it, from how you see it here. The one that's all A's and C's is all n1 and n3. And there's no n2 here. So we're only using 2 of those locations to get those faces. God, we're going to be doing this GRE thing forever. So it's going to keep doing that, where we can use these lower dimensionalities to always be able to describe what's going on in the higher dimensionalities. Because we're just going to partition different numbers. And when we start looking at, like, okay, what does this look like in notation? All of this stuff right here, this is a plus b plus c parentheses to the n. Or to the r. Yeah, how many flips we're using. So all of the different possibilities here end up getting us a plus b plus c all raised to the r. We can extend this to 4 dimensions as well. It gets much harder to draw. However, the first one is just 1, right? So r equals 0 when d equals 4 for a dimension. Okay, which means that over here, d equals 3. Up here, d equals 2. And d equals 1 is extremely boring. It's just 1 all the way through, because there's only one thing you can do. Okay. So with our dimension being 4, r equals 0 is going to get us just a 1. There's only one thing that happens. You get nothing. In r equals 1, what we have is a 4-sided die. So, you know, a tetrahedron. This is the D4, if you will. You throw that, and somebody ends up stepping on it, invariably. What happens here is you've got one of 4 possibilities. You go in the A direction, the B direction, the C direction, or the D direction. And then we could also, like, draw those in as as a shape to it. All right, r equals 2. So now we have 2 rolls of the same tetrahedron. We end up with, if you get 2 in the A direction, there's only one possible way to do that. If you get 2 in the B or C direction, or in fact D direction, there's only one way to do those. But now you got the possibilities that you do 1 in the A, 1 in the B. Again, there are 2 different ways to do it. It's either AB or BA. Same with all the others. So now it's 1, 2, 1 in every direction. So now you've got your AB direction going this way, your AC direction going this way, your BC going this way, BD, CD, and AD going that way. I forgot a 2 in there. So this starts getting much harder, and again, this 4-dimensional object is actually connected. So that single 1 compared to the tetrahedron that's all 1s, compared to the tetrahedron that's all 1, 2, 1s, those are actually connected in a 4th dimension. We just can't see it because we can't conceptualize it because we don't understand. Humans. If it doesn't help us swing from one tree to another, we're not going to understand what it is. Not always true, but generally speaking. Right, and then the same thing happens with then r equals 3. This is where things get complicated because you've got 1, 3, 3, 1, 3, 3, 1, 3, 3. And going back toward our D direction, we've got a 3 and a 3 here. We've got a 3 and a 3 there. We've got a 3 and a 3 there. And also, we have a number in the center, which is going to be 12, because it comes from all of the 2's around it. Those 2's are all connected to this middle number, which is the 12. All right, then it starts getting complicated. Wait, then it starts, yes, then it starts getting complicated. Because now you have to be able to see in 3D which numbers here are going to produce numbers on the next row down. Right, so graphically, as a picture, it's almost impossible. As doing math, it's actually almost trivial because you just have to know which connections are made. So this is the moment, more or less, when I realized I'm probably going to need a better notation system for this. And I'd heard a little bit about tensor calculus, and I was like, maybe I could use tensor notation to better start talking about like what rows and dimensions and the number of each n sub I that we're using for all these. Maybe we could put these in as subscripts and superscripts at the same time with some other stuff that's going in there. So I started learning tensor calc, for better or for worse. It doesn't really do what I want. More or less what I need is a new notation system to keep track of all of this. And it's practically impossible. I don't know that I know how to do it. So it would, I think, and I don't know that there is a proper way to do it. So it could be interesting to talk about, but this is more or less where I'm at in order to figure out, like, how to do this one. Again, this is now going to be A plus B plus C plus D to the R. Right, 0, 1, 2, and even 3 are not that hard to calculate, but then you've got to start to get into all the different ways that this is done. So, yeah, this is, like I said, this is where it starts to get hard. So I'm trying to figure out, there's actually something else that I'm trying to figure out personally, which had to do with the sum total of every row. So in this case, right, what is the sum total of this slice? Which 1, 2, 3, 4, 5, 6, 7, 8 is going to be 24, 27. So this is going to end up being our dimension raised to the r power. So here, this is 3 to the 4th. This is 3 to the 3rd. etc. Out of all that, there's also some really cool stuff that goes in there. Am I also doing probability theory? Not with this, but I can, because it's easily enough to be related to other stuff. Because I understand the multidimensional nature of the n-simplex, right, I can, in theory, calculate probabilities going out to any dimension you want it to go to. So, it's kind of interesting. Alright, we got a 3-minute ad break. I will be back very shortly. Tardlex, good evening, welcome. So sorry that I'm heading out. I'm not leaving, but just 3 minutes. Be right back. Thanks so much, everybody, for coming.
There's a beauty in the way you're worn, and the sharpness of your thorns. So vibrate in the imperfections. In the pain there's something real. All that anger so concealed. Still you're lost in how to feel. Just let me hold that severed heart. The pieces feel so cold. All the tears won't bring it back to life. But hate will always grow. There's a beauty in the way you lay.
Good evening and welcome. Welcome back, everybody who was here before. And so, Tardlex, yes, asterisk. I don't really answer like 100% the problem you're working on, but at the same time, if you give me something, I generally speaking have a way to teach it, and I will be happy to attempt to teach whatever it is in the way in which I typically teach it. I'm going to usually be aiming for, I want you to know why something works the way it does. Some people really rail against that because I am a huge pain in the ass. So if you are interested, we do also have a community Discord that we use. This is Penn Center. Who is a department chair at a college in British Columbia, in Canada. That is his Discord, but we use it kind of as a like math community Discord here on Twitch. So if anybody's interested, you can use that Discord link that way. You can use that Discord link, get in there, and we'll usually be either in the Maths Forum or the Maths Chat. So if you go to Maths Forum, you can post like your question and it'll be in a box. If you go to Maths Chat, it's just all inline chatting. So I also got a package. That's not there. I also got a package in the mail that is exciting. I have not played this particular game on stream because my system would grind to a halt. However, I am rather excited about Expedition 33. And so I managed to find a... It's downstairs. I'm gonna have to get it later. But I managed to find appropriate black suspenders. The Marinière shirt, the striped French shirt. There is a hat store up the street that sells red berets. And the round glasses, black jeans. I've got a pair of black boots somewhere. So I'm going... Oh, and a gingham... gingham, like, fabric. So I bought a couple of meters of gingham fabric, and gonna tie it up around myself, and we're definitely 100% doing a cosplay for Halloween, but also it works any other time. Oops. We're 100% doing this outfit right here. Now, I do not have hair that could rival that. However, maybe we'll just go with one of his other hairstyles. But yeah, 100%. This is what we're doing for Halloween. The arm is a bit trickier, naturally. I'm getting a compression sleeve, and I'm gonna figure out something to do either with gold paint, because we do have this one's sort of bronzy gold, but we do have some various paints that, like, if we figure out how to do it, we can make it work. and look like, you know, at least somewhat reasonable. So yeah, we're totally going with the baguette outfit, and we'll see how many other people will shout the game phrases at us from across the stray. Yeah, maybe we'll have to put like, I'll just have a bag of candy, like put some of mine in theirs and say, for those who come after. That doesn't work that way, but anyway. Alright, so I'm going to make something up, but it's going to be at least reasonable. When an oil spill expands on the ocean, it is 1 meter deep and roughly circular, right? If there's not too many currents or whatever, we're going to neglect all of those things. So, if a pipe bursts, leaking 20 cubic meters of oil per minute. How much will the radius be changing after 2 hours? Okay. So we've got something that actually... Right, it's going to be circular if you're looking at it from straight up and down. If you're looking at it from kind of a, you know, bird's eye view essentially, then what we have here is cylinders. Right, they are all 1 meter deep. And again, the volume of a cylinder is going to be equal to pi r squared times the height of that cylinder. Since it is all 1 meter deep, then that h is just going to be 1, so this makes it rather nice, right? H is going to be a constant. So this problem is going to reduce to our volume is going to be equal to pi r squared cubic meters. Just a little bit weird to look at, but it's fine. You just have to remember what's going on with our h. We can make this a much more complicated scenario if you really want to, but no. Don't do that. Okay, so h is going to be a constant. Our volume is going to be related to the radius, and then we know that the derivative of the volume dv dt is going to be equal to a positive 20 cubic meters per minute. So how do we get dv dt? Oh, look at that. We need to derive this particular equation by, or with respect to t, time. So we end up with dv dt is equal to pi. Here, we're taking, constant there, we're taking r squared and taking its derivative. So that's going to be 2r times the derivative of r with respect to t, dr dt. Dr dt is the thing we want. So when we get dr dt, it's going to be equal to dv dt divided by pi r squared. Nope, that's not right. Whew. Sorry. Divided by 2r and pi. That's all in there. Okay. That is not a pi. That is supposed to be an r. My goodness. I'm okay, I promise. Dv dt divided by 2 pi r. Alright, is going to be equal to our dr dt, which is what we eventually want to find. So we do know for a fact that dv dt is just going to be a constant throughout this whole process. It's just plus 20 cubic meters per minute. No, what are you doing? Right, 20 divided by 2 pi r. Okay, so r is the only thing that we actually need in order to figure out what the change in the radius is going to be, because we already know what the change in volume is going to be. We just don't know what the current radius is, and we don't have that information either. It's not given to us. However, we do know that we have 2 hours and we have a volume equation. And we have a dv dt. So taking all of this information together, we could say that, okay, after 2 hours, we had 120 times 20 cubic meters per minute. Again, this is 120 minutes. So our minutes divide out, and V at 120 is going to be equal to that. So this is going to be 2400 cubic meters. It's going to be V at 120. Okay, so then V is equal to 2400, which is equal to pi r squared. So what's r? Now we have to figure that out. So r squared is going to be 2400 over pi. And r is going to be the square root of that. 2400 over pi. We can divide out 400, which becomes 20 on the outside, times 6 on the inside. So 20 root 6 over the square root of pi. So then, going to look at the last step here, and we say now this r belongs in there, which means that dr dt is going to be equal to 20. We can make that 10 over 1 instead of 20 over 2. Right, 10 divided by pi times 20 root 6 divided by root pi, which, right, this is going to make into pi to the 1/2 in the denominator. So dr dt is equal to, here we got 10. It's going to be 2 root 6 in the denominator, 1 over root pi times 2 root 6, which is 1 over 2 root 6 pi, which is approximately, as long as I get an exact answer for my students, as long as I get an exact answer, having the approximation is just kind of nice for like double checking real quick. You have to rationalize it. Oh man, crack me up, Zach. No, I know you probably get a lot of those. 2 root 6 pi. I was kind of on that camp for a while, where I was like, well, you know, you really should do it. And in a lot of cases, even if you tried, you would fail. I mean, yeah. Is the square root of pi rational? No. All right, approximately 0.11516. Good enough. Meters per minute. So we're looking at 115 millimeters, right? Or, no, not 100. Jeez. Yes, 150. Man, I'm okay. Yeah, 115 millimeters. Not very large. Give or take, right? 11 centimeters every minute. I mean, that's still pretty big, given that this is like, what is R anyway, right? So you go 20 root 6 over root pi. That's 27 and a half meters. So that's still a very large amount of distance. I mean, not like, you know, obviously not kilometers, but it's like here down the road a fair distance. And it's changing this much every minute.
The setting on your razor, and whether the party actually is fancy thing you should
right?
check is your Experian credit report.
So
Especially if
that's
you're looking
actually
for a brand
alarmingly
it
fast,
lets you
given how
understand
much
what they're
volume
using,
there
so you
is.
can increase your chances
Granted,
of getting the best
as
deals.
the radius
It's
gets
dead
bigger,
easy to check it
the
and completely free.
change in the radius is
See
going to start
details.
shrinking,
Download the Experian app
but you're still
today.
pumping the same amount of oil into a larger space. Square root pi over pi. Oh, yeah, the tracking nonsense. As a calculus teacher, I'm very pragmatic about it. What's more expressive and useful in context, yes. Yeah, didn't you know pi's 3? It's mandated. Indiana legislature tried to make pi equal to 3. That was a bad week. It was also in the 1800s, so don't have to worry about it too much, at least right now. PD argument. Oops. Professional development. Oh, yeah. Yep. God, that's so... I couldn't even imagine. As both a pre-calc and calculus teacher and, differential equations and also basic math, I taught the gamut. I did not... There were individual classes I never taught. Right, never taught stats. Never taught business calc. Never taught... The teacher's ed courses I never taught, which really, I think I should have. I think I definitely would have, knowing the Liliadol stuff now. I would have been like, I want that class. I mean, literally, as much as you can, model it. Be like, hey, look, it worked even for not math. Just have to change its form a little bit. Yeah. Yeah. And I mean, realistically, I would... That was an elementary ed class, the one that our community college had. Because I think the secondary ed ones are at the universities. And I don't know that they actually. I don't think we had the opportunity. I think it was always like considered a higher level education class. Maybe junior or senior. It was a senior level class at UNH. This shirt is from when I moved in 2001. And it does not have a single hole under the armpits. It does not have a single, like, hole around the collar. It does not have anything. This shirt is old enough to drink. Like, and it was given to me for free. Every freshman who went to, I don't remember if it was the orientation week that was, halfway through the summer or whatever, or if it was during our orientation week that was during, like, the week before everybody else got there. I don't really care, one or the other. It's been 25 years almost. They gave us all a coupon in our package, whichever orientation this was. And it said, go down to Hayden Sports, which is the name of the place on campus. It's downtown, so it's like a little ways out of the way from where we were staying. But it was right across the street from my dorm, which was downtown in Durham, New Hampshire. Now I say downtown. Wonderful, I have to say, right? Wonderful place. It's like large town. It's basically, it's a lot actually kind of similar to what we have here, only this town that we're in is like, edging its way to very small city. And in England, things are a bit different than they are in the States, but nonetheless. Durham, New Hampshire is a, like, large town, small city, and it was just so wonderful because you could walk downtown without too much of a hassle. Our dorm was literally right across the street from a couple of, like, shops, shop areas. And, like, if you lived on the opposite end of campus, you had to walk. I mean, it's not that far, but still, it was a good 10 to 20 minute walk to go downtown. We were 2. And, so Hayden Sports was, like, right there. And everybody just handed in this coupon. And, of course, UNH paid for it because, like, whatever, it's good publicity. Again, 24 years later, this shirt is doing great. I have 3 t-shirts, which are currently downstairs in a pile, awaiting for me to remember, oh, right, I need to do that, to sew up, like, 2 or 3 holes, 2 of which I've already done this before. Because just wearing them and, moving around and doing all this stuff, it just wears out the stitching, and the stitching comes undone. Like, these companies need to... I mean, I know what it is. The companies are going for planned obsolescence or whatever, so you have to buy another one. But... but, like, literally, I have worn this shirt once a week, roughly speaking, for 24 years. And it's doing great. It's a little thin, but honestly, it's fine. I actually sent them a picture. I think it was during COVID because I was bored. But I was like, hey, this is the, like, 20th anniversary of me getting this shirt. thanks so much Hayden Sports for having quality products. I don't know if they still do, but nonetheless. We also went there before we came here to England in 2024. Yeah, it was like March, and we were moving in April. So we went up to New Hampshire to say goodbye to everybody, and we went to UNH because we're like, I need a new UNH sweatshirt, right? Like, and a bunch of other stuff. So like the kids, both of our kids got a sweatshirt. I mean that trip cost us a lot of money, but nonetheless. And I think we got a blanket or something like that too. So, you know, all branded UNH. But like she and I both went there for our undergrad. I don't know that she ever got one of these shirts, but we both got shirts for when the new dorm was going up on this side of campus. It was the suite dorm. Had all like 4-room suites that were all the entire thing. But they were pounding piles when we were like starting our freshman year. So, you know, you'd have the pile driver out back just bring the weight up and clink, clink, clink for like 4 hours a day. And me and my roommate are just sitting there with the windows open like, so when are they done? Yeah, so it says, I survived the construction. I almost never wear it because the back of it is all one panel, and it's really hot in the summertime. So you just sweat directly into, you know, the screen printing stuff, which is plastic. So it's just like you're just sweating right into plastic. Like it doesn't get the heat off of you. Anyway. Well, so like, yes, right? Of course, everybody has been under the I survived the construction thing for college, but the thing was that, like, the pile driver was less than 200 feet outside of my window with nothing between us. So there's a big difference between that and the people who were at the freshman dorm quarter mile away who couldn't hear it. Or maybe they could hear the echo of it coming over the, you know, through the buildings and stuff. But they could not see nor hear what was actually going on a minute-by-minute basis. There were plenty of times, and there were plenty of times when I chose to go somewhere else on campus because of this. And like, okay, it's not terrible. But it's one of those things, right? I just want to go back to my room. I just want to like take a nap. I just want to, you know, whatever. I just want to do this. I just want to go back to my room, play video games. Mood. You know, I just want to do this, and I can't because the construction is going to interfere with my thoughts, with my enjoyment, with whatever. So it was fine. It turned out fine. But of course, it was just a matter of like, I could not do my preferred activity because there is a massive construction project happening pretty much right outside my window. Yeah, well, the other reason I don't wear it that much is like, it says like I'm a survivor on it, and I was like, that's kind of minimizing of a lot of other things that are going on in the world right now, being that I started school in September of 2001. And a lot of other things, and I was just like, yeah, that doesn't feel right. So it sits in my closet. I'll wear it occasionally. It's kind of alongside the Dunder Mifflin t-shirt that I have. Anyway. Alright, so there's a lot of other cool examples that we can use with... Wow, that just jumps right to indefinite integration. Yep, right there. Literally next page. And I guess, like, it was probably the actual next section in my calculus classes, but still. It's just a little surprising, I guess, that we're technically there already. Yeah. So the basic idea behind like all of the related rates questions right? Find an equation to relate the known quantities that are here, and then derive with respect to usually time. Ooh, sorry. Okay, still, it may be another variable, but almost always, right? It's going to be with respect to time because we're talking about a particular rate. So we're talking, again, meters per second, cubic meters per minute. There was just all that stuff we were doing over there. Just whatever it is that you're looking for. Solve for the target rate and then plug stuff in. Right, and then find we're gonna plug in find the unknown values using the other equations that you have laying around, and then solve and explain using context. So in the related rate here, we were talking about the oil spill, right? How much will the radius be changing after 2 hours? Our radius will be increasing by, again, 11.5 centimeters every minute. Something like that. .115 meters per minute. Right? Most people are not going to care about the ridiculous minutia that would go into a more precise answer than that. We just don't need it. There are some people who might take exception to what I'm saying there, but Phil. Okay, So integration. For the most part is still, because this is the GRE book, it's assuming that everybody knows how to do integration, and therefore here's just the overview of it. It doesn't really explain everything about how to make it work, and how, like, Riemann sums, or at least not yet, how Riemann sums are related to integration, how it's area under the curve, you know, all of that stuff that we build up during the Calc 1 class. So I will go over at least some of it for anybody who doesn't know how integration works. If that link to the Discord server did not work, let me know, please. Because there are other links, I just don't have them. I know Zach's got one. So most of the time that we look at indefinite integration, we also call that anti-differentiation, because it is literally just reverse what you did for differentiation. Notationally, really what we want is to see something like this. We see y equals 3x squared. If we want to do the antiderivative of this particular thing, most of the time we would take the, again, antiderivative. We do this integration notation, and we say that if we take the integral with respect to x on both sides, the right-hand side, this is the derivative of the function x cubed, and over on the left, this is the derivative of some other function that we're just going to call capital Y. Right? It can't be y, and because we're because we're integrating with respect to x, it's not going to be it's not going to be a factor of y squared. Right? We're not going to be saying, oh, what's the antiderivative of y? Doesn't work for us. Right? So since these are different variables, specifically y is a function of x, then this is going to end up becoming capital Y. We do this all the time with stuff like the antiderivative of f of x dx is going to be capital F of x. And there is one little caveat to that, and that is that if we were to take the derivative of x cubed, we get 3x squared. If we take the dx, if we take the derivative of x cubed plus 7, we get 3x squared dx. If we take the derivative of x cubed minus 2 times 10 to the 20th power, we get 3x squared dx. So all of these are the same. When you take the derivative of something that has x cubed, and then we add any constant we want on the end of it. We always get the same derivative. Think about why that is for a minute. Right, we all talked about this during the derivative section. The derivative of the constant part is 0. Or, we're looking at this in terms of what is the slope at any particular value on this particular function. If I shift it up or I shift it down, the slope doesn't change at all. Right? The slope is always the same as it was before we shifted it up and down. So that doesn't affect it at all. So here what we do is we say, okay, the antiderivative of 3x squared dx is going to be x cubed plus some other number. It has to be a constant. We don't know what it is, so we just call it c. Be done with it. All right, and we let it be a capital C just because it's of the integration type. So like, you know, our y got capitalized, so our c, our constant, is now just going to be a capital C. It doesn't really matter as long as you know that, yeah, okay, this has to be some sort of constant or vertical shift. Because again, we can shift that function up and down as much as we want, and it does not affect what its derivative was. Okay. Now, when we do this antiderivative stuff, and we start with something like, okay, y is equal to 7x squared minus x plus 1, something like this, then what can we do with it? Well, again, if we just take the antiderivative of each of the pieces, or rather, of both sides, with respect to x, the left side again becomes capital Y. The right side, much the same that we did the derivatives, we can also do the integrals separately. So this is allowed to be the integral of 7x squared dx plus integral of negative x dx plus integral of 1 dx. Okay. The integral of 7x squared dx, if we do antiderivative, what we need here is actually not the 7 itself, but rather we need, like we saw up above, a factor of 3 that's sitting in front of the x squared. And when we talk derivatives, it doesn't really matter what it's multiplied by. So 3 times the derivative of f of x is going to be the same as the derivative of 3 times f of x. It doesn't matter where the constant is. So we're able to move that in and out without any problems. The same is going to be true for integrals, and there's further reasons for it, but basically it's a limit, and it's a sum. So sums and limits, both you can take constant multipliers out. No worries. You can also separate them by addition and subtraction, as long as you account for where those pluses and minuses are. So 3 on the outside and f of x dx on the inside is going to be the same as the integral of 3 times f of x dx, all on the inside. All right, so that's a helpful hint for this. we can say, well, that 7 doesn't need to be there because it's not useful for an antiderivative. What is going to be necessary is we need a 3 multiplied by our x squared dx. I can't just make a 3 appear out of nowhere, so what we have to do is balance it by multiplying by also a 1 over 3. Here, we've got a -1 attached to that x, so multiply a -1 out front. That's fine. Again, here, x dx is not by itself a direct derivative of anything, but 2x dx is. And again, we need a balancing multiplier of 1/2 sitting up front in order to make sure that that now works. And then here, the integral of 1 dx is just x. And then also we have a constant value that's going to come from the third term. I know some of you are like, wait, don't worry about it. We'll get there. First term here is going to be 7 over 3. Multiplied by the antiderivative of 3x squared dx is x cubed. Plus c1. Again, constant number 1. Minus 1/2 times integral of 2x dx, the antiderivative is going to be x squared, plus c2, plus x plus c3. Alright, now if we're being super strict about this is going to be 7/3 x cubed plus 7/3 c1 minus 1/2 x squared minus 1/2 c2 plus x plus c3. Let's move all this around. So 7/3 x cubed minus 1/2 x squared plus x plus 7/3 c1 minus 1/2 c2 plus c3. Question. What's that? It's just a constant. So we're just going to rename it. We'll just call it plus c. That's fine. Some people are like, well, wait. We created all these things up there. It doesn't matter. Right? We did not multiply any of those c's by an x term. We did not pretty much do anything with any of those terms. We did not do anything with any of those constant terms anywhere from the top all the way down filtered to the bottom. So in theory, what we could have done was said, hey, look, we're going to take this whole derivative here, and eventually at the end, we're just going to get a plus c. That derivative. Take that integral. Take the integral of all of this stuff all together. And that whole term is going to come up with a plus c at the end. And we don't have to worry about individuating every single one of them so that they're all different from each other. Who cares? Again, there will be scenarios where some of these end up getting multiplied by x's and other stuff like that. And you do have to keep those separate from each other. But the fact is that in this case, it doesn't matter. So we end up getting 7/3 x cubed minus 1/2 x squared plus x plus c, just as a constant. If we look at the original, right, this is just the antiderivative of that stuff that was up there. The only thing is that, like, all of those terms that we were missing, right, are just going to end up in the denominator of any terms that they're missing from. So Some people might argue that it is a useful thing to say the antiderivative of n x to the n minus 1 dx is going to be equal to x to the n plus c. Other people might also be interested in saying, well, the integral of x to the n dx, let's start from this place, is going to be equal to, well, this means that we know that our exponent ended up increasing by 1 because it's the opposite of what the derivative does. The derivative decreases, so the integral, the antiderivative, must increase. So this is going to be x to the n plus 1. And then the constant, we had an n, it became a 1. What can you multiply that makes n turn into 1? Well, it's going to be 1 over. In this case, though, it was the new exponent. So 1 over n plus 1 times x to the n plus 1, all plus c. So either way you want to go with this, right? Our antiderivatives, our indefinite integration makes it look like this. Right? Effectively, we took our n that we started with and we divided by our new exponent, which is n. So now n over n is just 1 out front. On the bottom one, we started with a 1 and we divide by our new exponent n plus 1, so 1 over n plus 1 times x to the n plus 1 plus c. So however you want to organize it, this is what it all looks like. How are we doing? We're at 12:30. That's a lot of coffee left. There's a lot of coffee left for 12:30. It's all good. I have a final battle to get to in Expedition 33, so, like, let's go. Okay, so we've got a few different rules here. Anytime that we have any particular antiderivative that we know of, something that you know a rule for, you can undo it by doing this indefinite integration. It's just that usually we try to make it look like the derivative-antiderivative pair that we're trying to go for. So, like I said here with this polynomial stuff, we had, instead of 7x squared, we could make this look like 3x squared dx, and then take its antiderivative, which is just x cubed plus c. And again, our constants are all going to be weighted compared to what we need to add, or well, what we need to multiply in order to change it into the thing we want.
There are some things you should always check, like the hygiene rating on your local takeaway.
And again, other option is going to be just divide by our new exponent. So we're going to get a 7, which was already there, over 3 times x to the third. So, right here, 7 over 3, x to the third. Whichever way you want to make that work, it works. Okay, so we've got all of the rules that we had from before. We had our...
Using creative flavors inspired by your favorite tasty treats.
Yeah, okay. No, that's fair. There's a caveat here, a rather big one, is that n... Oh, gross. I got to do them separately because these are two different numbers. Curses. All right, so for this one, n is not equal to 0. It'd be weird. So n is not 0, and for this one, n is not -1. Right, the issue with this one being that, yeah, we'd end up with a 0 in the denominator of the new thing, so obviously that doesn't work. And we did talk about what happens when we had the integral of, well, x to the -1 dx. Right, this is integral of 1 over x dx. What derivative is this? This is just a derivative-antiderivative pair with the natural log of x plus c. If n is -1, it has this special rule because it belongs to the natural log stuff. Right, now there's all of these other antiderivatives. We'll just go through with examples. I'm not going to go through all of these. It's kind of ridiculous. Okay, so if f of x is equal to 6 root x minus sine of x plus secant squared of x right, capital F of x is going to be equal to the integral of all that stuff. Dx. Alright, so when we take, again, antiderivative of all this stuff, we've got 6 integrals of the root of x dx minus integral of sine of x dx plus integral of secant squared of x dx. So for this one, we're going to look at this and say, okay, root x is x to the 1/2. So if we take the antiderivative of that, hey, wait, that worked with the one that we just saw up above there. So this is going to be a 6 divided by x to the, add 1 to the exponent is going to be a 3/2, and then divide by the new exponent, 3/2. Okay, again, plus c minus the antiderivative of a sine of x dx, where do we get that from, is going to be a negative cosine. Plus c. Alternatively, we could bring in that negative and have left it there all along. The antiderivative of a negative sine is going to be a positive cosine. That's what we've got here. Plus, what is the antiderivative of the secant squared of x dx? Well, this is a tangent of x. And then again, plus c encompasses all of the constants that would have come from all of these other terms. Okay, so here we can divide our 3 out. Now this is going to be a 2 divided by a half. It's going to end up being a 4. Again, here we can multiply by 2 over 2. That 2 gets rid of that 2, and then we get an extra 2 for the top. Right, so 4 x to the 3 halves plus cosine of x plus tangent of x plus c. Another question popped up in here which said if f of 0, capital F of 0 is equal to 2, find capital F of x, which is the whole thing. So here, if we know that f of 0 is equal to 2, then we know that c has a definite value. At least, most likely, right? If there's some other quirk that's going on here, like it's the square root of something, or if it ends up with 2 possible values, it is in theory possible, not very likely. Then, c could have 2 different values, maybe. As I said, not very likely. So f of 0 is 2, which is equal to 4 times 0 to the 3 halves, plus the cosine of 0, plus the tangent of 0, plus c, right, equal to 2. So 2 is equal to 4 times 0 to a power is still 0, plus cosine of 0 is 1, plus tangent of 0 is 0, plus c. So here we can subtract 1 from both sides. C is equal to 1. Therefore, f of x, capital F of x, is equal to 4 x to the 3 halves plus the cosine of x plus the tangent of x plus 1. So now instead of being a c, which could be literally anything, we now have a specific c value, 1, which is going to make this f stand out from all other possible f's. So, like, there's your quantum theory, really. Right, c is in a superposition. It could be any value you want until we observe that f of 0 is equal to 2 for this particular case, in which case the waveform collapses and there's only one possible f. Never thought you'd hear me bring up quantum theory and sorry.
There are some things you should always check, like the hygiene rating on your local takeaway.
Right.
Setting on your road. Party actually is fancy dress.
Another possibility would be something like, what is the integral of x squared times x cubed plus 4 raised to the 5th dx? Now, there are two ways to do this. One is that you could expand the binomial out to your whole 6-term sequence, multiply in x squared to every single one of them, and then go from there. The other is far more interesting and far more useful, and that is that you should note that if this is a compound, function, or rather composed function, I suppose, here we should look at this and say, if we let this be u is this going to be, roughly speaking, u prime? So in this case, right, u is x to the third plus 4, and u prime is actually equal to 3x squared. Nothing else. And here we have an x squared. So these are at least commensurate. They have the same sorts of things that are attached. And so we can work with the x squared that we have on the outside to become 3x squared from the u prime in the middle. So what we do is we say, okay, this is going to be that. We're going to get an x cubed plus 4 raised to the 5th power times, right, x squared dx is what we have. What we need is a 3. And then again, to balance it, we need the 1/3 on the outside as well. So now, when we look at this, we could say, okay, this is a 1/3 times the integral of, this is u to the 5th, and 3x squared dx. Okay, so one thing to note here. This is du dx is equal to 3x squared. Therefore, du is equal to 3x squared dx. When we have that, now we can list it as du. And here, if we have an integral that is u to the 5th du, well, nope, not that one. This is just going to be u to the 6th times 1/6. And then plus c. Okay, and then we just have to reverse this. So get out of, this is 1/18. U was x cubed plus 4 to the 6th, plus 1/3 of c is still c. So it's just a constant. We don't care what exactly we call it. Right, if you want, yeah, sure, this is not the same C as it was on the previous line, but, like, it's close enough and nobody cares. It did not matter in this case, right, without loss of generality. That's Cardo's music. Memes by Niviro. Okay. Anyway. Cardo is a former Microsoft engineer, I think, and did a lot of programming. I can't remember. I think he worked on, I can't remember what it was. He was working on a few games that were really big. I could have this completely wrong, but you should go check out his streams. He's usually late night US West, so like it was a stretch. I almost never rated him because being US East, it was like 2 a.m. before he even got on. So when I was actually working, it's almost a 0% chance. right? Without loss of generality, this is an arbitrary constant. Just call it c. It doesn't matter if you call it c up there or call it c down there, or you call it c in both places. Just as long as you acknowledge that, these aren't technically the same number, but they're just a constant. And you're not changing it in any meaningful way, which is really the important part. Okay, that's that one. Okay. So, 1 is going to be, for instance, if we have the integral of the tangent of x dx, there is no integral or derivative antiderivative pair which is going to get you tangent of x dx. It just doesn't happen. So when you look at this and you go, oh no, I can't do this integral, 1, yes, it is possible there are some integrals you will not be able to do. I mean, there are some integrals which you will literally never be able to do as long as you keep working in real numbers. That's going to be the part that blows your mind. We have seen Dawn at Dawn Factorial and Penn Center, who have both, and Zach for that matter, who have done complex analysis methods. So when you do complex analysis, you take the stuff that's in these particular integrals, you trade them out for complex numbers. You can do the integral within complex numbers, and then you translate it back to real numbers, and then you get an answer. And that is absolutely wild. I love it. However, this is not one of those. This one is actually very easy, because what you can do is say, what is tangent of x? Okay, well, I know that the tangent of x dx, according to my trig teacher, is going to be the sine of x over the cosine of x dx. Does that help? Okay, not immediately on the surface level, because again, you don't have a simple derivative-antiderivative pair here. However, what you have what you do have here is that we have a function which is in a slightly awkward place. And we have its derivative, which is in the numerator altogether. Now, it could be that this is like a cosecant in the denominator times dx or something else crazy like that. You can do that sort of stuff, right? You can shift things around until it becomes more convenient. So in this particular case, if we let cosine of x be equal to u, then du is going to be equal to a negative sine of x dx. Again, introduce a negative to this sine of x dx to make it negative. And then to balance it, we got to put a negative again on the outside. Please, 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 please do not say that negative du is equal to positive sine of x dx and trade it that way. Reason being, some people get in the very nasty habit of saying dx is equal to negative du over sine of x. And this makes me go a little bit frothy at the mouth. You are mixing variables. Now, I understand that if you were to do this in this particular case, it would actually introduce the negative, introduce the du, and it would divide out your sine of x's in both places. So everybody's happy, everybody's fine. Please don't do that. Because, again, it gets people into the extremely bad habit of not always doing stuff that will divide out nicely, and then you've got an integral that has two different variables at the same time. Never do that. Ever, ever, ever. Ever, 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 ever. Ever, 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 ever. Okay, I don't know how many times I need to say that. Just don't do it. So, what we've got now is this top part, right? Don't do that. This top part is going to become du over, and the bottom part is going to become u. Hey, that looks familiar. Right? This one is going to be a natural log absolute value of u. Now, you do need the absolute value in this case. I think I forgot it in the previous one. Because we were looking at... There. Right, natural log absolute value of x plus c. It is really important because here our domain is going to be all real numbers except 0. So our domain here needs to also be all real numbers except for 0. So make sure your domains match. Okay? Here, when you take the integral of sine of x, tangent of x dx, we separate it into sine of x over cosine of x dx. Do what's called u-substitution. Or just function substitution. Find out what its derivative, antiderivative version is going to be, and then take that antiderivative, which we end up with negative natural log of the absolute value of u plus c. Again, c could be a constant. It could be only positives. It could be only negatives, but you just have to watch out for what else is going on here. So the integral of tangent of x dx is going to be a negative natural log of the absolute value of u plus c, and then we have to say, all right, what was u? U was negative natural log of the absolute value of cosine of x plus c. All right, integral of x dx divided by x squared minus 4x plus 7. That's a terrible idea. Minus 7. Just in case. Now, it's going to be pretty obvious that in this particular case, you cannot work with the zeros of the thing in the denominator in order to figure out like a nice whatever. It's not going to work. It's not going to be nice. The good news is that we do have the major interesting part of the derivative of the denominator in the numerator. Right? We have an x, which comes from the derivative of x squared. Now, the derivative of the rest of it is going to be a constant. And we don't have that here. But we can eventually make this end up working out. We can eventually come up with something that's nice. And in fact, we don't actually need the x on the top. Okay, if you look at the available derivative, antiderivative pairs, right, go down your whole list. Right, if you go down the whole list, there is like a particular one that stands out here. Right, something with a square in your denominator. Yeah, that could work. Oh, you know what? It's fine. I might have messed it up. It's fine. We'll just get rid of that x. It's actually dealing with fourth degree polynomial. So it's saying like, oh yeah, we'll do x to the fourth minus 4x squared minus, you know what? Fine, we'll do it. That'll work. And an x there. Okay. There's something that we can do here. It looks kind of gross. That's fair. But according to what we have, right, there's only a few options. Here, what you probably want to do is to complete the square. This is going to come up back again in like differential equations when you're doing Laplace transforms. So there's a whole bunch of stuff that this eventually starts looking a lot like. Alright, if we do x to the fourth minus 4x squared, what we can do is to say we want something squared to get us, you know, kind of a nice value. And don't worry about the constant part yet. What we can do is we can say, if we do this as the integral of x dx over parentheses x, what's going to get you the middle term? Okay, x squared minus something squared. Right? Now, when we're doing the middle term of a binomial like this, then that second term is going to be multiplied by our x squared twice and added together. So here, it's going to be x squared minus 2 plus x squared, well, okay, x squared times negative 2 plus x squared times negative 2. So now we get a negative 4 x squared when we bring them together. Then the last term, if we look at what the last term is going to get us, the constant is going to be a plus 4. Right, we started with a minus 7, and then I'm just going to kick that along. Right, I'm just going to put that at the end. Okay, x to the fourth minus 4x squared plus 4 is going to be a square number, namely x squared minus 2 parentheses squared. Then we can't just add 4, so you also have to subtract 4. Right, make sure that it is a net zero change that you made from the step above. And yes, if you wanted to, you could have immediately jumped to, oh wait, that's a -4 minus 7. That's going to be a minus 11. That's perfectly fine. You could have done that. Okay, now that we've made that substitution, interestingly enough, now we have a u-substitution. So if we let u be equal to x squared minus 2, then du is going to be equal to 2x dx. Okay, we need a 2 out front, 2x dx, and now we need a 1/2 out in front of the integral entirely. Okay, so this is going to be a 1/2 integral of du over u squared minus 11. Whoops. That was not actually what I wanted, but you know. Huh. That was a mistake. What I meant to do. Okay, fine. Let's go back to the beginning. Let's make that a +7 after all. +7 minus 4 is going to be a +3. Okay. U squared plus 3 in the denominator. I mean, yeah, sure, it's fine. It would be still doable. It just, I don't want to do that as a part of this example. Okay, u squared plus 3 is a direct antiderivative of the arctangent of u over the square root of 3, which is fun. Okay, and plus c. So in this particular case, we end up with 1/2 arctan of u was equal to x squared minus 2, all divided by the square root of 3 plus c.
There are some things you should always check, like
Okay.
the hygiene rating on your local takeaway, the setting on your razor, and whether the party actually is fancy dress.
And the next one is the integral of cosine squared of x dx.
It lets you understand what lenders see, so you can increase your
Okay.
chances of getting the
Now this one, again, same deal as what we were talking about before, where there is no direct derivative-antiderivative pair for cosine squared of x dx. So in this particular case, we're going to have to use a trigonometric function in order to break down cosine squared of x. If you're like, good, I'll use 1 minus sine squared of x. Guess what? You're back in the same position. 1 minus sine squared of x also has no direct derivative-antiderivative pair. So here we've got to say, what else can we do with cosine squared of x? Well, if you remember going back, there was another... I did this in the trig stuff that we were doing a while back, right? Cosine of 2x is equal to 2 cosine squared x minus 1. So, this could be shifted around to make 1 plus cosine 2x all over 2 is equal to cosine squared of x. Ah, much nicer. Now this is also true when we take it to the other side and do what happens if we have sine of 2x. You know what? No, never mind. Sorry. What happens when we have sine squared of x inside of our integral? Well, here there's another one for this too. This is 1 minus 2 sine squared of x is equal to also cosine of 2x. So therefore, if we shift stuff around a bit, sine squared of x is going to be equal to, right, 1 minus cosine of 2x all over 2. Okay, in this case, right, we only need the bottom one. This is going to be integral of 1/2, if we split the terms, plus 1/2 cosine of 2x dx. Then here, if we take the integral of 1/2 dx, that's just going to be 1/2 x. Plus c, but again, we deal with that later. Plus 1/2 times the integral of a cosine is a sine. We have the 2x that's here, but then we need another 2 from the chain rule. So if you remember, the derivative of the derivative of sine of 2x is going to be cosine of 2x times 2 dx. So we need a 2 here, which means we also need another 1/2 here. So let's see, 1/2 x, right, plus c, plus 1/4 sine of 2x plus c. Okay. I think that is going to be enough for the night. That was kind of a lot of sections, so we're doing all right. So, for integrals, right, this is antiderivatives. Where you need to, in the Calc 1 integration techniques, number one is look at the trig functions you have, because a lot of them are trig functions when you start wondering, what is this right here? Look at it, see if you can split it up in a different way, see if you can then do some sort of u-substitution on one of those parts that gets you the other one as part of your du. You've got one of them as u, can you get the other as du? Here, completing the square is a useful sort of thing that you can do. And here, knowing your other trig stuff, right? Knowing your other trigonometric identities is going to help, because then you can break stuff down into smaller constituent parts and see if any of them have a nice integral. Again, in this case, right, we have these nice integrals for cosines of ax, right? It doesn't matter what it is. That a is going to come out front because we need it as part of our chain rule. Okay. For next time, next Wednesday we'll be going over integration by parts, which is basically just the product rule. That's all it is. So if you know the product rule for differentiation, you're going to be able to figure out the integration by parts for integration. It's not particularly difficult. It's just harder to like memorize, basically, is what it comes down to. Let's see. Do we have anybody? No. So we have Dr. Gold, who is in just chatting at the moment, but is still doing math and science problems. And then we got a whole bunch of people doing games tonight. So, Casey Snow Art, somebody who is doing, right. Well, she's doing art, but she is a partner candidate. So coming up on, coming up on the appropriate number of people and viewers and everything else. She's doing all right. We got 145 of 150 subs. Draw Me an Animal Marathon. Her art is very nice. Typically revolves around animals of some kind or another. And like I said, she's really close to partner. So I think we're probably going to go see her tonight. We got, let's see, Mabel Takes is a Canadian political commentator. Maddie Braun doing Metal Gear Solid Delta. Racodactylus doing Science and Tech. Also doing Partner Push. Nice. High Potential doing co-working. High Potential was in here earlier. Right. So, let's go check out Casey Snow. I'm trying to get her up over the hump to get into the partner zone. So, here we go. We are going to be back Friday night for Against the Storm, Sunday night for Satisfactory, Monday for more of Building Thinking Classrooms, next Tuesday for Nine Souls, and next Wednesday for this one, GRE. More GRE, cracking the GRE stuff. So, we'll see you all later. My name's Obi-Wan Pez. This is N Simplex Pachinko. Thank you so much for coming, and we'll see you next time. Have a good night.
50 free spins to use in your first 7 days, and 200 more when you deposit and spend 10